Displacement, velocity, and acceleration. So we are trying to now understand how to relate these things using higher order derivatives. It's a huge application of derivatives, and all these examples which I am now going to consider will remind you of real-time situations, and soon you'll start appreciating the application of derivatives. Now the way I've organized these videos is that we have a few communication questions. We started with the graphs so that we could visualize what's going on. And now we're looking into very simple numeric problems which will give you some idea about the numbers. And once you get all these concepts, then we'll have quick multiple choice questions to get you through the whole chapter in no time. So I would like you to spend at least 10 minutes on this video, understand the basics, and then quickly go through the multiple choice questions and answer them. Right? So that is the whole idea. Now, since I always limit my videos to half a page, I've split this question into 3 small videos. Okay, so this one is position of an object along a linear path is defined by s of t equals to minus 5t square plus 30t, where t is in seconds and s is in meters. Find the initial velocity. What is the total distance traveled in 6 seconds, in 10 seconds? What is the displacement in 6 seconds and what is the displacement in 10 seconds? Represent the displacement graphically. Correct. So let's try to answer this question now. So s of t is given to us, and s of t is minus 5t square plus 30t. And this equation, let's call this as equation 1. Now it says find initial velocity. So velocity is derivative of displacement, and so we find derivative of this equation, and what we get is minus 10t plus 30. And that is velocity, correct? So let's call this equation 2. Now it says find initial velocity. Now initial velocity is when t equals to 0. So that is what we are going to consider. And I have not really written what is the domain of t. I've left it open, right? For no reason, but just like that. Okay, so we have s dash, the first derivative of displacement, which is velocity here. So we'll say this is my velocity, correct? Velocity is the first derivative. Now if you want to find initial velocity, we are assuming that to be at t equals to 0, right? So that is v of 0 is equals to, we'll plug in 0 here, and we say minus 10 times 0 plus 30, and we get our initial velocity as 30 meters per second, right? It's important to write units in your answer. So I've just shown you work here. I'm not writing answers separately, but initial velocity is, now we can write here v0 equals to 30 meters per second. Now the second part is, what is the total distance traveled in 6 seconds and in 10 seconds? Part C is what is the displacement in 6 seconds and 10 seconds, and part D is represent the displacement graph. Okay, so these are kind of related questions. So what I will do now is I'll quickly move on to part of D, right? So that we have a graph on the side and we understand what's going on. So I'm just leaving space here, and we are moving on to a part here which is trying to show this displacement on a graph so that it becomes easier for us to understand what we are trying to do. So here to draw the graph of displacement, it's a good idea to write this equation in factored form. So what I can do is I can factor this and write this as minus 5t as a common factor between these two, getting t minus 6 as the other factor. Now t minus 6 indicates that we have a 0 at t equals to 6, and 5t indicates a 0 at 0 itself. So we have a graph kind of like this, and it's upside down parabola, and it goes like this, correct? Now here, as seen from the equation, this is 0 and this point is 6. So from the parabola, we know axis of symmetry will be right through the center, which will be at 3. Now, we don't know what this maximum displacement is. To answer the question, what is the total distance traveled in 6 seconds? We know this is 6 seconds. The motion is something like this. Body goes towards right side and then comes back, right? Because it's coming back to 0. But how much it goes and how much it comes back, we can only find once we know this point. Is that okay? So that means we need to find what is the displacement at 3, correct? So that is the first thing to find. So let's do that. So for that, we will write down S of 3. S of 3 indicates displacement at 3. And the reason, as you see here, is that is maximum distance a body is traveling in one side and then it's returning. So S of 3 from here will be minus of 5 times 3 times 3 minus 6, which is minus 3, right? And that works out to be 9 times 5, 45. So that happens to be 45 meters for us. Okay, so it is 45 meters, and let's say this is this point, 45 meters. Now, as you can see from here, the total distance traveled in 6 seconds should be that goes up 45 meters and then come down 45 meters, right? And when we say in 10 seconds, and we have to go further down and see, well, what happens at 10 seconds, correct? So let's extend this a bit more and see what happens. So solving questions is exploring. That is what it is. So let me extend this graph a bit further and draw a line here, and let's say this is the point. And let's say this is the point where time t is 10, right? So this is time in seconds on this side. Correct. So for that, let's find the displacement at 10. So when we write 10 here, so this is displacement, okay? 45 is the displacement. At 10, the displacement is what? So we'll plug in 10 in this equation, right? So minus 5 times 10 square, which is, let me write 10 square, right? Okay, we use that equation this time, that's fine. Minus 5 times 10 square plus 30 times 10, right? You could use either of those two equations, correct? So you get here minus 500 plus 300, right? Which leaves us with a number minus 200. So it is indeed negative, and it's like the long values, we just made a shortcut here. So it is, you could use either of the two equations. If you plug in here, then it is minus 5 times 10 is 50, and 10 minus 6 is 4, 50 times 4 is 200 indeed, and you get a negative sign. So we just break it a bit here, and we'll write this point as minus 200, okay? So this is at t equals to 10 for us. Now, so you got some idea about this, and from the graph we can see that the displacement is indeed 0 for s equals to 6, correct? So the displacement curve gives you some displacement ideas, right? Now let's write down. So s at 3 is 45 meters, at 6 it is 0, and at 10 it is 200. So these values will help us to answer part B of the question, right? So actually I should have written part B later on, but you know, the part C should have been answered first, which is what is the displacement in 6 seconds and in 10 seconds. So think like this. We are answering at present part C, okay? So we say, what is the displacement in 6 seconds? So we just plug in 6 here, right? So when you plug in 6 here, 6 minus 6 is 0. So we get displacement in 6 seconds is s of 6 equals to 0. And in 10 seconds is that s of 10 equals to, we plug in 10 here. We use the first equation this time and got this to minus 200, correct? So consider this to be before B. Okay, now that's a good idea. Now here we have displacement at 2 different times, and now let's continue with part D, which is represent the displacement graphically, right? So we're trying to now show displacement graphically. So you can see this is my graph where I'm showing displacement s of t on the vertical side and time independent variable along the x-axis, right? So here it is not that the ball is thrown up in the air, but it shows vertical linear path, right? So what I will do here is to show you a linear path this time. So this looks like a two-dimension thing, but let me just show you how it looks like a linear path. So assume that the object is here and starts moving. So when it starts moving, so for first 3 seconds, the object is going in this direction, right? This is happening in first 3 seconds, and we can write this that t equals to 3, and at that time displacement is 45, right? So 45 is your displacement at this time. Now after that it turns, right? So because I don't want to overlap everything, but actually it is this straight road along which it's moving, but I'm trying to show you phased out. So then it turns and it like kind of goes in this direction, right? So what you notice here that in another 3 seconds, when t equals to 6, it crosses the initial mark, right? So t equals to 6, but displacement equals to 0. It comes to its initial mark and then continues to move in this direction, right? It continues to move in this direction. And what we figured out that when time was 10, when t equals to 10, our displacement was minus 200. The displacement means you are talking with reference to a point, and that is our reference point. Do you understand? So at reference point, we have t equals to 0 and s equals to 0. So that is our linear graph, correct? And which truly represents object along a linear path, right? So that is how you can see. So what you also notice here that there is a turning point at t equals to 3. So when an object turns, so what happens to velocity? At this time, the velocity is 0. Do you see that? At this time, the velocity is 0. So velocity was 0 at, we have this velocity 0, velocity was 30 meters per second initially when we started with, but at this point, we find the turning point. So at t equals to 3, we have velocity equals to 0 also, right? Which you can check with your equation. If I write t equals to 3 here, right, in the derivative, then minus 30 plus 30 will give me 0, right? So it makes sense. So a turning point is a point where the velocity is 0, right? So this is how it is. And you'll also notice that velocity is, when you plug in the values, it was 30, right? When we started, 30 meters per second, and then it became 0 at the turning point, and after that it is negative, right? So we'll explore those parts later. Anyway, here we have represented displacement graphically in 2 different ways. Do you see that? Now this is kind of a graph which is xy coordinate system, and this is on a linear line, right? Now this actually helps us to answer part B. So I should have actually asked part B after representing displacement graphically. So it is, let's go through that now. What is the total distance traveled in 6 seconds and in 10 seconds? So that is what we are interested in doing now. So as you can see, now we will do part B, and that is distance traveled. In fact, in this video, that is the most important part which you should definitely understand. So the distance traveled is during the interval t equals to from 0 to, let's say t, 0 to 3. So distance traveled is from 0, right, to 45. So the next distance is 45 meters. Do you understand? So distance is always a positive thing. And then from time 3 to 6, again you found that the displacement at 6 was 0, at 3 it was 45, right? So it is from 45 meters to 0 meters, right? So we again covered a distance of 45 meters, maybe in opposite direction. That is immaterial. When we are talking about distance, it is a scalar quantity. We are talking about magnitude, right? Now that is one. So distance traveled in 6 seconds is total of these two, right? So which is 45 plus 45. And so we get 90 meters as our answer. Do you get the thing? So in 6 seconds, the answer is 90 meters. So 90 meters for part 1. Now what happened in next 4 seconds? That is, we'll consider from 6 to 10, right? So from 6 to 10, we see that the object is actually moving to minus 200 from 500. So from 45. So it is from 45 to minus 200, right? So the distance covered is difference of these two. Do you understand? So it is, displacement at 6 is 0. So it is from 0 to minus 200. So it's a difference of 200 meters, correct? So it travels another 200 meters in these 4 seconds. Do you understand? So the total distance traveled will be, in addition to first 6 seconds plus these 4, so which is plus 200. So that gives us 200 plus 90 gives us 290 meters, correct? So we get here the second answer, which is 290 meters. Do you understand? So total distance traveled in 10 seconds is 290 meters. That is how you find distance traveled. Now you can appreciate that these two things, distance traveled and displacement, are very, very different things altogether, right? So in 6 seconds, what you note is displacement is 0. This graph clearly shows you displacement. You started from initial point 0 and y displacement is 0. So this is your displacement time graph. Is it okay? So from here you can read displacement. At t equals 10, displacement is minus 200. At t equals to 3, displacement is 45 meters, correct? Distance is literally how much you go up and down. So you went up 45, came down 45. So in 6 seconds you traveled a distance of 90 meters, and then you went down 200 on the other direction. So 290 is your total distance. That is how you get your answer. I hope you understand that now. So both these diagrams will get us through this chapter, and every time when we have a word problem, you can think graphically like this, and which one suits you better depending on the situation, use them. Okay, so we'll move on with this example, and we'll have 2 more videos to understand more aspects on how position, velocity and acceleration are related. So it's worth spending 10 minutes on this, and then multiple choice questions will get you through the chapter in no time. Thank you and all the best.